Hi everybody. Here are the solutions for your practice book, section 8, topic 1, comparing linear, quadratic, and exponential functions. So this first part of this, I think, is really super easy. We're just comparing the graphs and identifying if the graphs are linear, quadratic, exponential, absolute value, square root, etc. And we've studied the three that they give us here on this very first page, so you should be really familiar with what these graphs are representing. So look at the first one. This should look familiar. Look at the second one. That should look really familiar. And look at the third one. We spent a lot of time on these. So the first one, what type of graph is this? Is it linear, absolute value, quadratic, exponential, or square root? And the obvious answer seems to be that's an exponential function. All right, look at this one. What do you see? It's a line. Gee, I wonder what that is. Yeah, that's a linear function. You guys are really familiar with those. All right, and look at part C. Here's our U shape. We're so familiar. We worked with those on 2 entire sections of our book, and that would be a quadratic function. So you should be able to recognize those 3. Out of curiosity, since they've given you absolute value function as a choice here, let's talk about that. Absolute value functions are V's. And square root functions look even funnier, and we haven't done many of those anyway, or looked at many of them. I'm not going to deal with those at the moment. All right, let's keep going to the next page here. So here's a quadratic function, right? We are familiar with our U's. Circle the word that correctly completes the following statement. The function represented in the graph above is exponential or quadratic. There you go, that's a quadratic function. And part B. The A value of the function. All right, and then look at this one, the C value. What are they talking about? The A value for this graph above and the C value for the graph above. So if you remember when we were doing quadratic functions, the standard form of a quadratic looks like this. Y equals ax squared plus bx plus c. It's been a little while since we've seen those. If you remember, the A value determined if it was smiling or frowning and how skinny or wide it was. That's what the A value's job was. And then the C value, just like as in linear functions, that's the y-intercept right there. If you remember, the y-intercept, that's C. All right, so let's talk about this again. Part B, the A value of the function that represents the graph above is positive, negative, or 0. Well, it's smiling, and if it's smiling, it's being positive. So our A value is positive, and we can tell because the graph opens up. It's smiling. Part C. The C value of the function that represents this graph is positive, negative, or 0. Okay, remember the C is the y-intercept. And here it is. What is our y-intercept? That is -3. So the answer here is it's negative because the y-intercept is -3. Negative. There it is. Write the equation that would represent the graph shown above. Okay, there are a variety of ways we could go about doing this. First of all, we know 2 different forms of the equation. We know standard form, but we also know vertex form, and that was what we were using to write the equations of these normally. So we're going to write it in vertex form because that's actually kind of easy based on the fact that this is a very nicely set up graph for us, but there is another way we can do it. We can change that to standard form, and there is another way we can go about writing it. So I'm going to try to show you all of these in this little space here on this page. So here's our first one, the one that we had done before. If we started our vertex, by the way, what is the vertex there? Let's see, it's 1, -4. Let's write that down. So the vertex is 1, -4. And let's look at how it's set up. From the vertex, over 1, up 1, go back, over 2, up 4. Does that sound familiar? That should. It's our parent type graph. the standard one. So that tells us our A value is 1. Over 1, up 1, over 2, up 4. It's just normal. So our A is 1. And with these two things, we can write our equation in vertex form. And it goes like this. Y equals A times x minus the x coordinate squared plus our y coordinate, which is minus 4. There it is. That is our equation in vertex form. But what if we wanted that in standard form? We can change it to standard form by doing a little bit of math here, a little calculating. So we're going to rewrite this. I don't need that 1 there. So we're going to rewrite it as, let me do it over here. Y equals, okay, what does x minus 1 squared mean? It means x minus 1 times x minus 1, something squared times itself, minus 4. And let's go ahead and multiply x minus 1 times x minus 1, and we do that by building a box. X minus 1, and we get x squared minus 1x plus 1. Be careful of that one. Negative 1 times negative 1 is positive 1. So now we have y equals, all right, let's simplify, or yeah, collect our like terms here. X squared minus 2x plus 1. And don't forget we had this minus 4 on the end, so we're going to stick that minus 4 on there. All right, now we can simplify this part right here, and we can write y equals x squared minus 2x plus 1 minus 4 is minus 3. So now we have our equation in standard form. Vertex form, standard form. There is one more way we could have gotten this right here. So let me show you this alternate method. Either one of these was fine, but our alternate method of getting this would be, let's look at our x-intercepts. What are the x-intercepts on our graph? Look at them up here. And I see that they're at -1 and +3. So we're going to write, well, -1 and +3. I can write my equation as y equals, all right, let's do the zeros here. The zeros of the function are -1 and +3. So how would we write this first one here? We'd write x plus 1. Why? Because that -1 plus 1 would create a 0, one of our zeros, and zeros are our x-intercepts, which are on our graph. So our second one is x minus 3, because remember, if we put that 3 in there, 3 minus 3 makes 0, and that would be one of our zeros, which is the same thing as our x-intercepts. Okay, now let's build a box and multiply x plus 1 times x minus 3. Have it write kind of small here. And we get x squared minus 3x plus 1x minus 3. Collect like terms, and we get y equals x squared. 1x minus 3x is -2x minus 3. All right, here it is in standard form, and I want you to notice something. Look at that. It's the same thing. So we had two different ways we could get to standard form for the equation of the graph above. All right, let's go on to the next page. There we go. All right, determine whether the rate of change for each function is constant or not constant. All right, the rate of change, that's another way of saying the slope of the line if we had it graphed. And we can look at tables to determine constant, not constant. But if you remember us talking about linear functions, exponential functions, and quadratic functions, we often talked about one of them having a constant rate of change, meaning it's traveling upwards or downwards at a constant rate. So let's see, the rate of change for a linear function. Okay, rise, run, rise, run, rise, run. Those are all the same, all the same. This is a constant rate of change. There it is. Okay, the rate of change for an exponential function. Okay, well, let's look at this. Our exponential function starts out kind of, going upwards kind of slowly, and then it, starts going faster and faster upwards. This is not a constant rate of change. Our little steps start looking kind of funky. So that is not a constant rate of change. The rate of change for a quadratic function, well, that's not constant either. Some of the times it's going down faster than other times. Some of the time it's going up. There's no way that this is constant either. So what's the only one of our graphs that has a constant rate of change? Linear. Linear is the only one with a constant rate of change. That's really important to remember, really important. All right, let's look at a table. This is a table that represents a quadratic function, so we're not going to see a constant rate of change here. What is the rate of change between the first and second point? All right, rate of change is the change in the outputs over the change in the inputs. The change in the y's over the change in the x's, or rise over run. Rise is the y's, run is your x's. So let's look at the change between the first and second points. So 4.5 is dropping down to 2 by -2.5. I kind of ran out of room there. And your y's going from -3 to -2 are going up 1. So the rate of change is -2.5 over +1, which can be simplified to -2.5. What is the rate of change between the second and third points? All right, 2 to 0 is a drop in 2, and -2 to 0 is a rise of 2. So your -2 over +2 simplifies to -1. So the rate of change between the second and third point is -1. What is the rate of change between the third and fourth point? That's your next question. So let's look at that. From 0 to 2 is going up 2, and from 0 to 2 is also going up 2. So we're going to see a rate of change that is 2 over 2. Rise 2, run 2, which simplifies to 1. Now we're going uphill because this is a quadratic function and it obviously was going down and now it's coming back up. All right, so between the fourth and fifth point, which is the last question, from 2 to 4.5 goes up 2.5, and from 2 to 3 is going up 1. So rise over run, or the change in the y's over the change in the x's, is 2.5 over 1, which simplifies to 2.5. All right, use the pattern of the rate of change to complete the table below that represents a linear function. So what are we going to see with a linear function? We're going to see a constant rate of change. Yeah, constant rate of change. Okay, so the first thing I always do is I look at my x's to see if they are listed one after the other. See, in the last table, they skipped over some, which kind of makes it a little harder to see patterns. So I like when they're not skipping over any, and it looks like they're not. We're growing by 1 every single time. -2 to -1. This is going up 1 to 0 goes up 1, up 1, up 1. We've got a nice list of inputs here. I like that. All right, so now we can kind of trust what we're seeing in the outputs. So let's see, from 8 to 5 goes down 3, 5 to 2 goes down 3, 2 to -1 goes down 3. So what are we going to keep doing here? Go down 3 and down 3. So from -1, we're going down 3 to -4, going down 3 more to -7. And by the way, what is our constant rate of change here? It's -3 over +1, which is a constant rate of change of -3. That's what we're doing. We're dropping 3 all the way down. This line we also know, because it has a negative rate of change, that's talking about its slope, it is going downhill. And going downhill pretty steeply because it's -3. There you go. That is the end of 8.1.